Okay, so I'd like to start where I finished last time. So last time we had seen the definition of a set. So here I'll give, we gave a preliminary definition. I'm going to give a slightly better one now. So a set is going to be a well-defined collection of distinct objects. Okay, so this was something that I didn't exactly clarify last time. Let me say one sentence first. So the objects are referred to as the elements of the set. As the elements, or sometimes the members of the set. So I think of them as kind of living. This is the object's home. So one thing which I didn't get into was the ensuring that this was distinct. So what I mean here is if I take the set, say circle, triangle, square, this is the exact same as the set circle, triangle, and square. So sets don't allow repeated elements. This is something that will, is kind of a shortcoming in some sense. We're going to see later that it'll be useful to allow situations where you allow repeated elements, but in this case, so far, we're just saying these are the exact same sets. So maybe just some notation here. I say we have triangle is in this set to mean that triangle is a member of this set, which I haven't named. Okay, so let me give an example now, kind of a very important example. So the empty set, which will always be denoted with this symbol, is the set with no elements. So which contains no elements. Okay, so you can think of this, remember last time we saw that sets can be thought of as yes-no functions. So as a yes-no function, what the empty set does is it just assigns no to every object. Sorry, so the way that you thought of a set as a function, you said, give it an object, and you ask it, is it an element of your set? Well, so the empty set always answers no. Okay, so just another way to write this, so for any object x, x, and this will be my notation, x is not in the empty set for any possible object that you have, and just more notation, we can write the empty set is the set with no elements in it. Okay? So let me play my favorite game now and do true false, which is the empty set equal to this. Okay, so I'm going to pause here. Okay, so the answer is going to be false. Okay, so the empty set is not the same as the set containing the empty set, which is the set on the right. So remember, there's nothing strange about sets having sets as some of their elements. That's just something that's allowed with this kind of general definition. So you can think of this again as, well, the empty set has no elements, but the set containing the empty set has elements, has one element, namely the empty set. Okay, so even though it seems like, there's nothing inside here, there is an object here, and it's the empty set. Okay, so let me give you some more notation, or really notation and a new notion. Okay, so given a set S, I'll usually write that for the cardinality of S, or sometimes I'll write this, so number S, which just denotes the number of elements of S. So the number of elements in S, so this is called the cardinality of S. Okay, so far this kind of makes the most sense when S is a finite set. Then I can just say, this is some number in the natural numbers. We're going to see you have to be a little more careful when you write infinite sets. Cardinality of S. Okay, so let's do a true-false. True, false. What is the cardinality of the empty set? Is it equal to 0? And what about the cardinality of the set containing 1, 2, and the empty set? Is this equal to 3? Okay, so the answer in both cases is true. So the reason is, well, the empty set has no elements. Right, so when I'm looking at the cardinality, I'm saying how many elements there are. Well, by definition, empty set has 0. This is different from the set containing the empty set. And this one is true as well. So notice that when I'm doing the cardinality, I don't care at all about what these elements are. So I could have chosen 1, 2 empty set. The 2 could be a tree. Doesn't matter. All that matters is the number of objects. In this case, so the empty set counts as good as 2 for an element of the set. So I get 3. Okay, so what we've seen, let me do a new concept. Okay, so we saw the idea of, well, I have a set, and I can look at the elements of the set. So generalizing set membership, what I can do is I can talk about relations between sets. So I can talk about subsets. Okay, so what is this? So let A and B be at this point just arbitrary sets. So we say that A is a subset of B. The notation for this is, we usually think A is contained in B, or sometimes I'll write B is contained in A when it's convenient. So if every element of A is also an element of B. Also, okay, so in other words, what I can say is if X is in A, then X is in B. Okay, so let's do some more true-false. There's just nothing better. So true-false, well, let's first do is the empty set contained in A? And the second one, if A is in A, then A is contained in A. Okay, so I'm going to pause here. Okay, so the solution to the first true-false is, so 1 is true. Okay, so this is a little strange, but let me just say why this is. So we have to check for every element, so we check for every element of the empty set that element is in A. Is in A. But there's no elements to check. So it's what's called vacuously true. Meaning, this is, and we'll see this whenever we're doing if-then statements. So maybe I'll just say what we saw here. Remember, containment is the statement if X is in A, then X is in B. Well, if X is in the empty set is always false. And we'll see more when we talk about kind of a little bit about propositional logic. Whenever you have an if-then statement and the if statement is always false, then the entire statement is always true. So what that means is that when there's nothing to check, then it's just going to be vacuously true. Okay, so what's the how about the second statement? So let me just so always false. So the if-then statement is always true. Okay, so let me do the second statement. So this is false. So why is this? Well, in this case, this doesn't just the statement A contained in A doesn't make sense. Okay, so the reason is, well, when I write this containment symbol, it's a relation between sets. A is contained in B, and A and B are sets. But it's not a relation between a set and an element of the set. Okay, so if I wrote this, so how could I make this statement true? But true if we replace A by the set containing A. Okay, so the set containing A is going to be a subset, and it's something to be careful of, right? So whenever you are dealing with elements, whenever you just have to be careful with what the objects are that you're dealing with. So when you're looking at containments, it's always between subsets. When you're looking at membership, there's always a set and then another element. So let me give you, so this is going to be a problem to talk about for the lectures. So on the lecture discussion session. So, and it's a very useful one. So the set A is equal to B if and only if, so exactly when A is contained in B and B is contained in A. And we'll see that this is actually usually the way that you show two sets are equal. You never really want to show that they just have the same elements. It's much easier to show that one is contained in the other and the other is contained in it. Okay, and we'll see that soon enough. So let me give you some more examples. Again, will be useful for writing out notation that I'm going to use for the whole class. So we have the set of the natural numbers is contained in the set of the integers. This is going to be contained in the rational numbers. This is going to be contained in the real numbers, and this is contained in the complex numbers. Okay, so let me I'll write out a couple of these just because I want to have some convention. So first, the natural numbers never contain 0 in this class, so it's going to be 1, 2, 3. The integers do. This is just positives and negatives. Maybe I'll say, well, The rationals, even now, I don't really want to get into it because it's, you have to be a little careful. I could write A over B, AB in Z, but then I have to be a little careful because 1/2 is the same as 2/4. So we'll see this soon. I won't even touch the real numbers or complex. So we'll see later. Okay, so let me ask another question, and I'm going to encourage people to pause again and work it out for themselves. So what are the subsets of the set containing a sphere and a torus? Or a donut. Okay, let me pause. Okay, so what are there's kind of two obvious sets, right? We saw that we should have, since these are elements, so the sphere is an element of this set, so the set containing a sphere and the set containing a torus are certainly both elements. And then we have kind of the slightly trickier ones, or the ones that you have to kind of remember. So we said the empty set is also an element, a subset, always a subset of any set, and also the set itself is a subset. Ugh. So if I write what are the subsets of sphere and torus, I don't know why my sphere got smaller there, I have to include the set itself. Okay, so usually these are referred to as the proper subsets. So in some sense, they're kind of the non-trivial ones where you get more interesting information. And then there's always the case that S is contained in S, and the empty set is contained in S for any set S. Okay, but you have to kind of always remember to keep those in there. Okay, so let me give you a generalization of what we just did. Okay, an important generalization. So let X be a set. The power set of X, which is going to be denoted by P of X, is the set of all subsets of X. Okay? So, for example, what we just saw here, I could call this set S, and this would be the set P of S. Okay, so let's do an example. So please think about this before I tell you the answer. So what is the power set of the empty set? Okay, so I'm going to pause. Right, so let's work this out. So first, the power set is a set, and the elements of that set are the subsets of the empty set. So I'm going to write it here, just the brackets first. So what are the subsets of the empty set? Well, it's just the empty set. Right? So the empty set is a subset of the empty set, completely trivially. So the power set of the empty set is the set containing the empty set, right? So it's not, the power set of the empty set isn't just the empty set, it does have an element because the empty set is a subset. All right, here's a kind of a fun one to now do. If I look at the power set of the empty set. Okay, so what is this? Well, it's going to be a set. The subsets or the elements of it are the subsets of this one. So what are the subsets of the set containing the empty set? Well, it's the whole set, the set itself. And then we have to remember that the empty set is always a subset, right? So the empty set is a subset here, and the set containing the empty set is also a subset. So we have to get inventive with the number of brackets that we have. So it's going to be the set containing the empty set and the set containing the empty set. And you can continue this as much as you want. It's kind of, I would maybe write if you have fun / boredom or out of boredom, you can do some more examples, do a couple more iterations. And actually work out the cardinality. That'll be useful later. Okay? We'll see it later. Okay? So this is actually one way that set theorists can build the natural numbers from scratch, or just from set theory in some sense. You have the empty set, and then you're allowed this power set. Well, the empty set should probably be, maybe call it 1, and then this could be 2, call this 3, and then you've built the natural numbers just by completely just completely basic set theory. Okay, so let me do another, I would say, more interesting example. And now this I do want you to really consider before I tell you the answer. Well, I won't even be able to tell you the answer. Okay, so I'll just give you a little hints. So I have the natural numbers, which is 1, 2, 3, ... What is the power set of the natural numbers? Okay, so I'm going to pause here, think about it, and I'll have the answer soon. Okay, so let me write down a couple elements before I get, started with trying to describe what this power set is. Okay, so first we can write down, well, we know like the empty set is in there, we know the whole thing. These are both, elements of the power set. I could also, just you give me any collection numbers. I could write, 1, 3, 8. Google, this is a perfectly good element of the, it's a subset of the natural numbers. So I could write, just give me any finite list of natural numbers, and then just from there I give you an element of the power set. So that's pretty big, but of course we can get bigger, right? Because you can think, well, there's also infinite subsets. So I could look at, say, the odd numbers. So the set containing the odd numbers is an element of the power set. I could also just come up with something totally random, right? 1, 4, 20. It's hard to come up with random things. 100, 174, ... This will be a perfectly, whatever, there's no pattern, just choose some random numbers. This is, oops, sorry, so I've already messed up I'm going to, okay, so I have to erase this. And this one. Okay, so these should have been, the set is of odd numbers is an element of the power set, not a subset. Apologies. Okay, so what else could, and then the world's your oyster, right? Just come up with whatever random, sets of natural numbers that you can come up with, and those will all be elements. So let me just give you a way to think about them, and we'll see that this is actually a pretty good way to think about them. Let me start with a real number. I don't know, I'll give pi. Right, this will be, well, I don't really know much of pi. 3.14159.2. I don't know. Okay. And now how do I associate this, an element of the power set of the natural numbers, well, what I can do is just take this entire decimal expansion and chop it up into bits, and those will be natural numbers. So I get, this one could be 3, then I get 14. I want to make sure that they're all distinct, so I get 159. Keep going as you would. So I get this element of the power set from a real number with a decimal expansion. So I have to be a little bit careful because, I could have a number like I don't know, 3.14014. So this is a slight issue. Right, because then I would write 3, and then I would write 14, and then I would write 014, which is 14. So you have to be a little bit careful, but after being careful, it turns out that the power set of the natural numbers has, has the same number of elements as the real numbers. Okay, so I have to, these are both infinite things, so you have to be very careful. But basically, for any real number, I'm going to be able to find a set or a subset of the natural numbers and vice versa. Okay, so we will see much more of this later. Okay, so now let me, so we've seen kind of ways to compare sets now. So now what we'd like to do, I guess I can move all this. So we've seen ways to compare sets. And now what we want to do, now we want to combine them. Okay, so, these sets are the building blocks of math, as far as I'm concerned. So, obviously, if you have blocks, you want to put them together, right? And you don't want to just say one set's bigger than another. You want to, build something more exciting. Build a new set out of two old sets, okay? So, let's do this. So, we want to combine them. So, so I have to be a little careful here. One thing that's going to be useful for us is, so I'm going to do this in terms of Venn diagrams. And what I'm always going to assume is that A and B are both subsets of a set U, which is going to be some universal set. Okay, this is kind of technical, why you need this, but you'll see, quickly when I draw some pictures why it will be useful. Okay. So let me give you kind of the pictures that you'll be seeing. So we imagine that there's a set U, there's a set A, and a set B, and these are, so the elements of A live in here, the elements of B live in here, and then, there might be elements that live in both, there might be some elements that live in neither, and what we're going to do is just basically make a definition for each possible region that you see in this picture. Okay, so we'll see things like the set of things contained in both, or maybe the set of things in one but not the other, and so on. Okay, kind of everything you could imagine. Okay, so let me start with just kind of the first definitions. So let A and B be sets, which are both contained in a universal set U. So contained in a set U. Then we're going to define what's called A union B to be the x in U. So this is why it's kind of useful to have this set around. So I can say where the sets, or where the elements live, right? They're all elements of U, and they satisfy the condition that x is in A, or x is in B. Okay? So, i.e., the set of all elements in A or B. Okay, so let me just mention here, or in mathematics always means and or. Okay, so whenever I say you're in A or B, you can be just in one, you don't have to be in both. You're still good. Okay? So for example, if I look at the set containing the empty set, forgot how to draw my double hole donuts now. There we go. Union, the set containing the empty set. So this is going to be, well, I look at the elements that are in either one of these sets. This one has the empty set, this one has empty set and what's called two-hole torus. And so I just get empty set and two-hole torus. All right, so let me give you another definition. So I have A intersect B. This is defined to be x in U, where x is in A and x is in B. Okay, and what this means is that both have to be true. So both true. The set, so I look at the elements that are in A and in B. So in the past example, I get that the empty set and my two-hole torus intersect the set containing the empty set is now just the set containing the empty set, because the two-hole torus isn't in both. You can write, as I said, so this would be, maybe I'll put the union here. This is my picture for union. I guess I had already kind of done it there. This is A union B. This would be A intersect B. I'll do more, but maybe I'll just write one more. A minus B is going to be elements, x in, oh, I guess I can write that. Yep, that's okay. X is in A. Don't even need U. Where x is not in B. Okay, so that was my picture here. Okay, and we'll see a lot of more of these constructions basically on the homework. And okay, so that's all for today. Thanks.